Hello, good morning everyone, or good day everyone. I am Joshua Ryan L. Empistan, and welcome to the evolution of CPU processing power. Today, we will embark on a journey from the foundational silicon of the 1970s to the architectural marvels that power our modern world. We'll start with deconstructing the core principles of how a central processing unit or CPU operates, transforming simple electrical voltages into complex digital experiences we rely on. Then we will trace its revolutionary evolution, exploring the key innovations in design, memory management, and multitasking that allowed a chip with just 2,300 transistors to evolve into a billion transistor engine executing over 18 million instructions, or 80 billion rather, instructions every second. This is not just about faster clocks, it's about the ingenious engineering solutions to bottlenecks in speed, power, and complexity that have shaped the digital age. So, next. So, for the introduction, the CPU, or we often call the CPU the brain of the computer, but this analogy is limited. Unlike a brain, the CPU does not think, learn, or understand meaning. It is a meticulously precise, ultra-fast instruction processing machine. Its intelligence is an illusion created by software. What makes the CPU truly impressive is its evolution from 46,000 instructions per second to over 80 billion, an increase of nearly a millionfold. And understanding this evolution is crucial because it explains the why behind everything from software system requirements and performance bottlenecks to the very structure of our operating systems. It reveals how hardware and software have co-evolved in a relentless push for greater power and efficiency and capability. So let's start with the part one, the binary representation using voltage. So at the start, or at the absolute heart of all digital computing lies a simple, robust concept, which is the binary representation using voltage. Inside a CPU, everything, so every number, every letter, every instruction is reduced to a pattern of two states. One is a high voltage, or typically represented by the value of 1, and a low voltage, uh, representing or represented by the zeros. So this binary bit is the atom of computing. Using only two states is an engineering masterstroke because it creates clear, non or noise resistant signals that can be transmitted, stored, and manipulated with extreme reliability. Every complex operation you see on your screen, from rendering a video to calculating a spreadsheet, is at the physical layer. The orchestrated manipulation of billions of these tiny voltages switches every second. Next is the bit, bytes, and the words. So, uh, while a single bit is powerful as a concept, it's practically useless alone. So, to represent a meaningful data, we group them. For an example, we have 8 bits to form a byte, and it is capable of representing 256 unique states, enough for all English letters, digits, and symbols. So when a CPU processes data, it does so in chunks called words. And the word size is core to a CPU's architecture. So word size is core to a CPU's architecture For an example, the Intel 4004 used a 4-bit word, while modern CPUs use 64-bit words. But the question is, why does size matter? Size matter because a larger word size allows the CPU to handle more data per operation, represent vastly larger numbers. A 32-bit word can represent over 4 billion values, and critically, access exponentially more memory. So the move from 4-bit to 64 bits is a direct map of computing's expanding ambitions. Next is the instruction concept. Simply, the CPU doesn't understand Python, C++, or any high level language, but it understands only its native instruction set, or a fixed vocabulary or of primitive commands. Each instruction is a unique binary pattern that commands the CPU to perform an elemental operation like add these numbers, move the data from here to there, jump to this other instruction. A program like a web browser is simply a sequence of millions of these instructions stored in its memory. The entire list of instructions a CPU supports is its instruction set architecture, or ISA. This is the fundamental interface between the hardware and software and its design, whether reduced or complex, or RISC or CISC, has been the central battleground in CPU evolution. Next is the heartbeat, or the heartbeat, which is the fetch, decode, and execute cycle. The CPU's core operation is a relentless three-step cycle, which is fetch, decode, and execute. First, it fetches the instruction from its location in RAM by placing addresses on the address bus and reading the data bus. Next, it decodes this binary word, breaking it into an opcode, or what to do, and operands, which is what to do it to. Finally, it executes it executes the command by configuring internal circuitry like the arithmetic logic unit, or the ALU, to perform the operation. This loop is synchronized by the CPU's clock. In early CPUs like the 4004, this cycle was straightforward, but as we'll see, overcoming the bottlenecks in this simple loop, particularly the slow fetch from memory, drove decades of innovation in caching and pipelining. Next is the CPU clock signal. So, gluing the fetch code, decode, execute cycle together is the CPU clock, which is a steady, repeating pulse that synchronizes every internal operation and communication with external components like RAM, the RAM. Clock speed is measured in hertz, or pulses per second, is a fundamental driver of performance. The Intel 4004 ran at 740 kilohertz, while a modern CPU runs near 5 gigahertz. That's nearly 7,000 times faster on a clock pulse basis. However, pure speed hits physical limits. Higher frequency increased power dissipation and heat dramatically, and the clock period must be long enough for the slowest instruction to complete. This led engineers to seek performance gains not just from faster clocks but from doing more work per clock cycle through architectural advances.